everybody. So in today's lecture, I'm going to go over the test 2 review for Physics 2010 in fall of 2021. First of all, please remember that if I can't read it, I can't grade it. So you don't have to be, Pablo Picasso with your beautiful, gorgeous handwriting or anything, but just make sure that I can read it and that I can follow it, and then it's laid out in a linear, logical fashion. Also remember that if you don't show your work, I'm really grading you on your work, not your answer. And if you don't show your work, I can't give you partial credit. And if you don't show enough work, then I really don't know if you just guessed or what. So make sure to show your work. Also remember that you have to write units and your vector notation has to be there or I'm going to deduct points. We're covering chapters 4, 5, and 6 of matter and interactions on this test. We did skip the material and rest energy and the relativistic stuff because that's covered in your modern physics class separately. We did cover polar and cylindrical coordinates, which is in our supplementary text in section 11, chapter 1 of Introduction to Mechanics, and example 1.8 on page 18 of Intro to Mechanics. And that is from the Coding Circular Motion lecture. And we supplemented Chapter 6's Energy Principle and Matter Interactions with derivations covered in Chapter 5, Sections 1 through 3 of your supplementary textbook. Remember that I don't test on computational skills. On this test, there will be one derivation. It'll be one of the ones on this list, the amplitude of a simple harmonic oscillator, given both initial amplitude and velocity or the phase constant of that, the centripetal force formula, the work kinetic energy theorem in one dimension, or the formula for gravitational potential energy. And that's the one for Newton's law of universal gravitation, not MGH, not here on Earth. Okay, so that's going to be on there. You do get, I didn't say this, you do get one note card, 3 by 5 inch, for an equation sheet. So you can bring that in, an index card. Okay, so I'm allowing you that. Remember that I don't allow tablets, PCs, or cell phones to use as a calculator. Just regular calculators are allowed, okay? All right, so let's get into the material of it. Chapter 4, this was kind of a long chapter. In this chapter, one of the focuses was to model bonds as springs and the atoms that are connected by those bonds as little balls. And you can then use that model to figure out the origin of certain forces like normal forces, tension, friction, and so on and so forth. And we did that in this chapter. We figured out the packing density of materials to determine the equilibrium length of the springs in the bonds. Remember how to do this. We did multiple homework problems on this. Basically, it just involves using the density of the material in grams per centimeters cubed and then doing a unit conversion using things from the periodic table. Remember that a periodic table entry looks like this in the upper right-hand corner. This is the one for copper. The 29 means that there's 29 protons in copper. That's the atomic number. And then you have the atomic weight down here. And for copper, it's 63.55. So that means that for copper, each atom is 63.55 atomic mass units. And then you can also, because of the way that we set up the conversions, read off that there's 63.55 grams per mole of copper. Okay? Now, one atomic mass unit is 1.66 times 10 to the minus 27 kilograms. And Avogadro's number is 6.022 times 10 to the 23rd. Avogadro's number is the number of constituents in 1 mole of a substance. So there's 63.55 grams in 6.022 times 10 to the 23rd atoms of copper. All right? Okay, now the first thing that we modeled was tension, and we explained the tension force by talking about the ball spring model. Remember that tension is a pulling force that can be applied by a rope, wire, chain, something like that. And you can model it as the stretching of atomic bonds using Hooke's law. So to do this, we talked about springs in series and in parallel. So if you think about it, each one of these little chain of atoms is kind of like a bunch of springs in series. And we talked about how the effective spring constant for a bunch of springs in series is the spring constant for the total, or the spring constant for one spring divided by the total number of atoms in the chain, okay, or springs in the chain. And then for parallel, the effective spring constant is N times the number of chains. So here, for example, you have 9 chains that are basically in parallel, and then each one of these chains has 1, 2, 3, 4, 5, 6, 7. So you can figure out the total from that. So you can calculate the effective spring constant or stiffness of one bond from the tension force and the amount of that the rope stretches. So be sure to review those example problems in the notes. All right, we talked about stress and strain. Tensile stress, we usually use the Greek letter sigma to symbolize. And a stress is a force divided by a cross-sectional area. So if you're tugging on something like you can see here, this is placed in tension, being pulled either way, then the stress, because caused by that force that you're applying, F sub t, is F sub t divided by A naught, and A naught is the cross-sectional area. Okay, so you can see that indicated here in blue. Now that stress produces a change in the length of the material, which we'll call delta L. And in material science, they talk about the strain, which is delta L over the initial length L. And then, because it's related to Hooke's law, the stress and strain then are linearly proportional to one another. And in our text, the proportionality constant is symbolized by Y, the Young's modulus. So we write that the stress is equal to Young's modulus times the strain. And then if you break that out into a long form, that would be the tension force divided by the cross-sectional area is equal to Young's modulus times the change in length divided by the initial length. And you can relate Young's modulus to the stiffness of one bond in this way. Y is equal to K over D, where D is the length of one bond, okay, or the distance between the atoms center to center. Okay, we talked about free body diagrams. A free body diagram is a pictorial representation of all the forces acting on an object. So we're using the point particle model of an object here, which assumes that all the forces are concentrated at the center of mass. Now the normal force and gravity are symbolized here with the red and the black arrow. You don't have to be a good artist to do this. You can represent objects by dots. Remember that the length of the arrow is supposed to indicate the magnitude of the force. Sometimes that's tough to do. Remember not to forget to put the arrowhead on there so that when I look at your free body diagram, I can see that you understand which way the force is pointing. If you just draw a line to symbolize the force, that doesn't really help me very much, okay? So when you solve problems with Newton's laws in these free body diagrams, the first step is to draw a sketch with the forces labeled on it and indicated as arrows. And then for each object in the problem, you draw that free body diagram showing all the forces, making the magnitudes and directions as accurate as you can. You label each force, and if there's multiple objects in the problem, you have to draw a separate free body diagram for each force. Once you've done that, you choose your origin along in your sketch, okay? And then you can use that origin choice to resolve your vectors into their component parts. Once you've got all your vectors written out into their component parts, then remember that you're going to apply Newton's second law to each component separately, okay? We assume here that the forces' directions are independent of one another. So the forces in X will sum to one thing that's independent of the forces in the Y direction. And then once you've done all that stuff, you solve. Remember that when you apply Newton's second law, what you're basically doing is that you're saying, for example, the sum of the forces in the X direction is equal to one of two things, either 0 or the mass times the acceleration in X, okay? And then you do the same thing for the Y and the Z, or whatever directions you're solving for. Okay, we talked about some other forces. We talked about friction and the difference between static and kinetic friction. So remember, static friction is between objects that are not sliding with respect to one another, okay? So static friction acts to keep the object from sliding. I guess I should say sliding or slipping. That's probably a little bit more accurate. Remember that for static friction, your static friction coefficient, or your static friction will be equal and opposite to the applied force always until your applied force exceeds the threshold needed to start the object moving, okay? So that's why there's this less than or equal to sign here, all right? Also remember that your frictional forces are proportional to the friction coefficient times the normal force, okay? The normal force here, of course, is straight up. It doesn't have to be if the object is tilted at an angle, remember that your normal force always points perpendicular to your surface, okay? So for static friction, you have this less than or equal to sign in there. Oh, and one more thing. Remember that when you do static friction, that this is the friction that would be, hopefully, in between your feet and a surface when you're walking or running, right? You don't want your foot to slip on the surface. Or if there's a rolling tire or something like that, it should be the static friction that is acting in between the tire surface and the road. If it's not the static friction, then that means your tire is slipping on the surface, which means your wheel is spinning, which is bad, okay? So remember that. Okay, kinetic friction. The force of kinetic friction acts when an object is in motion. Basically, I should say slipping over another surface here, okay? Now, mu k, the kinetic coefficient of friction, it can vary with speed, but we're going to neglect those variations and just assume that it depends on what the surfaces are that are in contact with one another. And remember that your magnitude of your friction force, F sub k, is equal to the kinetic coefficient of friction times your normal force magnitude. Okay, we talked about sound waves. Sound waves are longitudinal waves. That means that the oscillation is parallel to the direction of propagation. There are compressions and expansions, which are called rarefactions, of the medium through which they travel. And you can think of it as a pressure wave. Remember that pressure is force over area, and the SI unit of pressure is the Pascal. And the compressions and expansions are caused by the vibrations of the atoms within the medium. So if there is no medium, then you're not going to hear any sound. We refreshed really quickly on the ideal gas law, which is PV is equal to mkT. Here P is pressure, V is volume, N is the number of molecules, K is Boltzmann's constant, and T is the temperature in Kelvin. Boltzmann's constant is given here, 1.38 times 10 to the minus 23 joules per Kelvin. So the pressure wave in the sound is caused by that localized change in the number of atoms per unit volume if you rearrange the law. Okay? So we talked about the speed of sound in a solid, too. That was for a gas. This was the speed of sound in a gas. We talked about the speed of sound in a solid, too. If you remember the Young's modulus of the material is y and the density of the material is rho, then d is the spacing in between the atoms. Then you can say that the speed of sound in the solid is equal to the square root of Young's modulus divided by the density, which is also going to be d times the root of k over m, okay? Where k is your spring constant and m is the mass of an atom. Okay, now remember that your speed of sound is proportional to the square root of your elastic property divided by your inertial property, which is your Young's modulus divided by your density. In a liquid or a gas, though, you can't pull on a liquid or a gas, but you can put them under a pressure, a bulk pressure. So we use, instead of the elastic modulus, the bulk modulus. The bulk modulus is defined here. It's equal to the change in pressure divided by the change in volume divided by the initial volume, okay? So you can write the speed of sound in a liquid or gas this way, too. V is equal to the square root of V over rho, the bulk modulus divided by the density. But remember that for liquids and gases versus solids, in air and most liquids, the molecules are so far apart and so loosely bound that the spring analogy doesn't really work anymore. And in fact, in ideal gases, we say that the molecules aren't attracted to one another at all. So in that case, in liquids and gases, the real difference there is due to the packing. We did a lot of calculations with density in this chapter. So just remember that the density rho is equal to the mass divided by the volume, m over v. The SI unit for density is kilograms per cubic meter. We often worked in grams per centimeters cubed. It's useful to know how to easily convert between those two things. So you end up multiplying by 1,000 to convert between grams per cubic centimeter and kilograms per cubic meter. And you can work that out in the derivation. And remember that water has a density of 1. I'll give you that, but, you know, it's useful to remember that water has a density of 1 gram per cubic centimeter, which is 1,000 kilograms per cubic meter. Remember that the formula for the pressure change as you go down some depth in a fluid is delta P is equal to rho GH, okay? Rho is the density of the fluid, G is the acceleration due to gravity, and H is the height between depths. And this describes the pressure difference between two levels of the same fluid. Remember that this is also the cause of the atmospheric pressure that we're experiencing right now. So you're basically just under a lot of air, which we model as a fluid. Also remember that 1 atmosphere of pressure is 1.013 times 10 to the 5th pascals. This is a conversion that I would give you on the test, but it's useful to remember that pressure units are strange, okay? Pascals is the SI unit of pressure, Newton per meter squared. Atmosphere is a little bit more intuitive, but then there's all these other units that were originally based on how the pressure was measured, the measuring device, okay? Okay, now if you have an object submerged in a fluid, then it's going to experience a force called buoyancy, and it's due to the fact that the pressures at the top and the bottom of the object are different due to the change in pressure as you go down in depth. So the buoyant force is equal to the mass of the fluid that is displaced by the object times the acceleration due to gravity, and you can look at that derivation there. Okay, so that sums up Chapter 4. Moving on to Chapter 5, we did a lot of free body diagram problems and a lot of vector problems. So we're determining forces from motion. Remember that one of the first things that we did was to find the dot product or scalar product to 2 vectors. The dot or scalar product is how you multiply 2 vectors and you end up with a scalar. Okay, so A dot B, the magnitude of A dot B is AB cosine of theta, and theta is the angle in between A and B. The scalar product is commutative, so A dot B equals B dot A, and it also obeys the distributive law. A dot B plus C is equal to A dot B plus A dot C. Remember that we talked about our unit vectors. The I hat, J hat, and K hat vectors are for the X, Y, and Z directions respectively. If you do the dot product of a unit vector with itself, you get 1, but if you do the dot product of a unit vector with any other unit vector, you get 0. Because of the cosine theta term, they're perpendicular to one another. And so we can express the dot product in this way as well. If you use your component form, and A is AX I hat plus AY J hat plus AZ K hat, and then basically the same thing for B, then A dot B is the X components multiplied times each other, plus the Y components multiplied times each other, plus the Z components multiplied times each other, okay? We talked about the polar coordinate system, and it's shown here. The polar coordinate system, instead of giving x, y as the coordinates, gives r theta as the coordinates, where r is the distance from the origin, and theta is the angle that swings counterclockwise from the plus x-axis to the position vector. Okay? You can easily convert in between polar and Cartesian coordinates using the equations shown here. X is equal to r cosine theta, y is equal to r sine theta, and then you can convert back and forth from that. Okay? And it's just because the x and the y components will form the legs of a right triangle where r is the hypotenuse, and so that's why you can use all those equations. But in order to use x is equal to r cosine theta, remember that the angle has to be swinging counterclockwise for the plus x-axis for that to work. All right, now we talked about how force can change a particle's direction or its speed, right? So a force causes a change in the momentum of the object, right? So the momentum, though, has a direction and it has a magnitude. And so either one or both of those can be changed by a force. So the force's components parallel to the particle's direction causes change in speed, and we call that F parallel. The force components perpendicular to a particle's direction cause changes in direction. So we wrote a force as the sum of the parallel and perpendicular components. F is equal to F parallel plus F perp. Now, if you write that in Newton's second law as dp dt, right, then that means that you'll have a dp dt parallel and a dp dt perp. Now, you can write P, or any vector really, as the magnitude of the vector times the unit vector that points in that direction. So P hat, right? So if you take the derivative of that, then you can apply, I believe it's called the chain rule in calculus. I always get my nouns mixed up. But if you do that, then you'll have a dp dt, that's a change in your speed, times p hat, plus p times dp hat dt, okay? Now, the dp hat dt, that causes a change in the direction. So this component here in blue is F perp, and this component here in red is F parallel. Now, we applied this to derive the equation for the centripetal force, and you should review that. But remember that for an object to be in uniform circular motion, which means that the speed does not change, that there must be a net force acting on it, okay? And that means, because the velocity is constantly changing direction, that's why there has to be that net force, that centripetal force points inward, which is always perpendicular to the instantaneous velocity at any given point. And we say that this centripetal force is mv squared over r. And as you can see here via the red arrow, it always points radially inward towards the center of the circle. Okay? Now remember that the centripetal force is not a force in and of itself. It must be supplied by something else. In this picture, the centripetal force is being supplied by the tension in the string that's holding that ball in the circle. Okay? If it's a car going around a curve, it'll be the friction between the tires and the road, and so on and so forth. Remember that we can write the speed also in terms of the distance divided by the time, which is 2 pi r over t, where 2 pi r is, of course, the circumference of the circle, and t is the period of motion, which is the time that it takes to complete one circle. Okay? We talked about the angular quantities. We talked about the angular displacement, which is delta theta, and that is the angle that it travels through in some instant of time, and that's the difference between the final and the initial angle. We talked about the average angular velocity being omega bar, or omega average, which is delta theta over delta t, the amount of angle that you swing through in a given amount of time. And then, of course, that would be for taking the limit delta t goes to 0, d theta dt. So omega is d theta dt in instantaneous angular velocity. Remember that all of these angular quantities should be reported in the SI unit of the angle, which is the radian, okay? And that there's 360 degrees in 2 pi radians, and 1 radian then is 57.3 degrees. You don't have to remember that conversion. You should be able, honestly, to remember the conversion that, 180 degrees is pi radians, or 360 degrees is 2 pi, and go from there. You should be able to remember that. Okay, you can also have an angular speed that changes in time. If you have a finite amount of time that you're tracking that angular speed change, then your average angular acceleration would be delta omega over delta t. And as you shrink delta t down to very small values, that gives you your instantaneous acceleration, alpha, is equal to d omega dt. Okay? Now you can relate the angular and the linear quantities in the following way. A displacement could be written as s is equal to r theta. This is the arc length equation. The speed could be written v is equal to omega times r, and the acceleration, if there is one, a tangential acceleration, would be alpha times r. Okay? Okay, chapter 6, the energy principle. So just remember, first of all, that energy is conserved. This is very important conservation law in physics. Now, that doesn't mean that an object can't lose or gain energy. It just means that energy, if the energy of an object changes, that it didn't come from nothing, that it was transferred to or from that object. So energy can't be created or destroyed, and if the total amount of energy in a system changes, then that's because the energy has crossed the boundary of the system by some energy transfer method. Okay, so a push or a pull into the system could change the energy and increase it, right? Or decrease it, and then the friction or drag can suck energy out of a system. Okay, we talked about the work done by a constant force. That work is equal to F dot the displacement. So you take the force vector that's pulling on it, here this woman tugging on the rope, and then you do the dot product of that with the displacement the object undergoes. So you can see here that the SI unit of work and energy is the joule, and it's a Newton meter, because if you multiply a force times the displacement, you're multiplying newtons times meters. Remember that only components of the force that are parallel to the displacement do the work because of that dot product that's there. So it doesn't have to be a constant force that does work. In general, if the force is non-constant, you can write it this way. It's the integral of F dot dr, and then you integrate over the path. The kinetic energy of a particle is due to its motion. The kinetic energy is often symbolized by capital K, and it's 1/2 mv squared. You can also write that as p squared over 2m, the momentum squared, divided by 2 times the mass. Here, of course, m is the mass of the particle, and v is the speed of the particle. kinetic energy is a scalar, and so you know that you must plug speed in there. Remember that a change in kinetic energy is one possible result of transferring energy into a system. And the work kinetic energy theorem tells us that the work done is going to be equal to the change in the kinetic energy of the object. Now, this is the total or net work, okay? So you sum over all the works, which means any force that could be acting on the system could have the potential to do work. So you sum over all of those, and then that equals to the change in the kinetic energy. If that net work is positive, then of course the kinetic energy will increase, and if not, vice versa, the kinetic energy will decrease. So if you're doing these work kinetic energy theorem problems, they can be kind of formulaic. Solving the work problems, you draw your free body diagram, you choose your coordinate system, you apply Newton's laws to determine any unknown forces, then find the work done by each force. And then to find the net work, either you find the net force and then find the work it does, or you find the work done by each force and then add. And then you have the sum of the works, and you set that equal to your change in kinetic energy and solve. Now, we talked a lot about conservative versus non-conservative forces. Basically, conservative forces keep energy in a system, and non-conservative forces transfer energy out of that system. Another way that you can tell the difference in between these things is that the work done by a conservative force is independent of the path taken by the particle, but vice versa for non-conservative forces. So the work done by a conservative force, if you're moving through a closed path, if you're starting and ending points at the same place, then that is going to be 0, okay, if you've got the closed path. Here, some examples of conservative forces are gravity and the spring forces. Friction and drag are examples of non-conservative forces. So we did a lot of derivations of the formula for the potential energy for different things. And we used this relationship here, which is just for conservative forces, and applied it. So what we said was that the work done by a conservative force is equal to minus the change in the potential energy. And then we solve for the work done by that conservative force, and then from there solve for the potential energy. So we could also say from that, conversely, that the force is minus the derivative of the potential energy, and you worked a problem for that. And that would be really true for any direction, not just x. So we talked about the gradient operator very briefly, but we'll get in more to that later, so don't worry about that too much for this test. One thing that you should worry about for this test, though, is the derivations of these potential energy equations and how to apply them in solving potential energy problems. So the universal gravitational potential, this is for objects, say, in space or something, where you're talking about the force in between two stars or a star and a planet or a spaceship or something like that. Then your universal gravitational potential energy, U, is equal to minus G big M little m over R. And, of course, R is the center distance between the objects. Little m is the mass of one object, big M is the mass of the other, and G is the gravitational constant, which is 6.673 times 10 to the minus 11 in SI units. The same could be said, they're both inverse square law forces, so they have much the same form. The Coulomb potential, which is the due to the Coulomb force, the force in between two positive or two negative or two unlike charges, that's U is equal to 1 over 4 pi epsilon naught times Q1 times Q2 over R. Here, Q1 and Q2 are the charge of the objects in coulombs, R is the center-to-center distance, and epsilon naught is the fundamental constant, the permittivity of free space, 8.854 times 10 to the minus 12 in SI units. These two potentials set the potential energy equal to 0 at infinity, okay? Now, some other conservative potentials that we derived were due to the spring force. So here, U is equal to 1/2 K times the displacement of the spring from equilibrium, here shown as delta S squared, okay? We also derived it as 1/2 Kx squared if you put the origin of your x-axis at the equilibrium position of the spring. And then for gravity here on Earth, we derived the function U is equal to mgh, all right? For multi-particle systems, basically, if you have more than one particle in the system, you just sum over all the pairs to find the total potential energy, and that's that. We talked about that related to the Madelung constant, and we did a homework problem on it. Mechanical energy and its conservation. The total mechanical energy of an object is the sum of its kinetic plus its potential energy. If only conservative forces act on the object, then you can set the initial and the final energy equal to one another, because there'd be nothing to change it if energy doesn't get sucked into or out of a system. Okay, so we only dealt with conserved energy in this section. We haven't done non-conservative transferring energy out yet problems. So when you do those kinds of problems, first you draw a picture, you determine the system for which energy will be conserved, you figure out what you're looking for and decide on the initial and final positions, you choose a logical reference frame, and you apply conservation of energy, E is equal to K plus U. Remember that there might be more than one kind of potential energy there. If you've got springs and objects, moving with respect to the ground, then you might have two there or something like that, and you have to include all of them. We didn't talk about that here. Let me delete that one. Okay, we talked about pendula. In general, this is the total mechanical energy of a pendulum. If you put the origin here down at the bottom of the swing, you've got 1/2 mv squared plus mgh. And remember that our trick here was that h is equal to L minus L cosine theta, where theta is the angle that the arm of the pendulum, whatever it is, makes with the vertical, and L is the length of your pendulum here, okay? Remember that your total energy is conserved, okay, for that one. Gravitational potential energy, the mechanical energy, was 1/2 mv squared minus g big M little m over r. Remember that in a bound system, the energy is going to be less than 0 there. And the absolute value of the potential energy is your binding energy, right? So that's how much you're bound. So that would be G big M little m over R. And if you have a kinetic energy that's equal to or greater than your binding energy, then that means your mechanical energy is greater than 0 and your object can escape. So if you've got enough kinetic energy, it can break free of that gravitational pull, but if you don't have enough, then it's going to be bound. If it's bound, if E is less than 0, then you've got a circle or an ellipse, and if it's greater than or equal to 0, then you've got a hyperbola or a parabola. If it's equal to 0, then that is the threshold kinetic energy that you need for escape, where your kinetic energy is equal to your binding energy, okay? And then from there, you can get the escape speed. The escape speed is shown here. You just set 1/2 mv squared equal to your binding energy, and you have the escape speed. So that's going to give you the square root of 2g big M over big R, right? So for example, you can solve for the escape speed for any planet, but if you're in orbit, what you would do is just plug in the distance that you are from the center to find the escape speed from that orbit. All right? Okay. That's my tobacco auctioneer's tour of what we did in chapters 4, 5, and 6. Remember that this review is not meant to be exhaustive, so you should go back over your notes. Remember that the best way to study physics is to work problems, work problems, work problems. So you should go back over your homework, make sure you understand all the homeworks. Make sure that you go over the practice test that I'm going to post for you. Make sure that you can do the practice test. Make sure that you can do those derivations that I cited. There will be a derivation on this test, okay? It'll be one of these, so make sure that you can recreate those. If you do all those things, you should be good to go, okay? So happy studying, and I'll see you in class.